Okay, so in this example, we are given that air is flowing through a 10 centimeter diameter pipe, and there is a long radius nozzle of diameter 6 centimeters, and we are asked the flow rate of air through this long radius flow nozzle. And in addition, we are given the upstream pressure, the temperature of the air, and the pressure drop across the nozzle. So, if you remember, a flow nozzle looks something like this, and there is a flow rate from this side, and then we have a sudden contraction, and we measure pressure upstream and at the throat, and the air comes out from here, but there is a recirculatory region like this, and because of that there are non-recoverable head losses. And if this diameter is small d, the throat diameter, and the upstream diameter is capital D, then the geometry ratio is beta, which is d by capital D. And in this case, the flow rate is simply given by the discharge coefficient multiplied by the area of the throat. In the square root, we have 2 times the pressure drop divided by the density of the fluid, and then multiplied by this term containing the geometrical ratio. So this is very accurate for an incompressible fluid, because in case of an incompressible fluid, the pressure drop, that is the pressure ratio P2 by P1, is close to unity. Because it is an incompressible fluid, there is a pressure drop, but this ratio is very close to unity. So let's say if P1 is 100 kilopascals, then your P2 will be somewhere around 99 kilopascals. So that there is a pressure drop, but this is a very small pressure drop in case of an incompressible fluid. But if we have a compressible fluid like air in this case, then the pressure drop P2 by P1 is much smaller than unity. So if you look, we are given a pressure drop of 60 kPa and P1 is 200 kPa. So basically P2 minus P1 is given, which is 60 kPa, and P1 is 200 kPa. So if you find out P2, you will get 140 kPa. So this is around a 30% drop in pressure, which is very significant. So we can conclude that we have a compressible flow in the duct and also through this flow nozzle. So in the case of a compressible flow, in addition to this discharge coefficient, we will have another factor y, which is called expansion factor, and this is often tabulated in terms of the pressure ratio across the flow nozzle, or an orifice plate, or a venturi, for different geometrical ratios given like this. So in our case, we are also given the geometrical ratio beta, because the initial diameter capital D is 10 centimeters, the nozzle diameter is 6 centimeters. So beta here is basically D by capital D, which is 6 centimeters by 10 centimeters, which is equal to 0.6. So for a compressible fluid, as I mentioned, the flow rate will be CD times an expansion factor multiplied by the area of the throat, and this square root term containing the pressure drop. So again, one another important thing to note here is that, so in case of an incompressible fluid, this density is constant throughout the pipe. But in case of a compressible fluid, the density is different here, the density is different here, just because there are significant pressure differences. And as you may know from ideal gas law, P equal to rho RT. So if P changes, rho changes a lot, and we are assuming a constant temperature here because in this problem the temperature is given to be constant and we will assume it to be T 100. So we will assume it to be a constant. So for a compressible fluid, we will just use the upstream density. That's why there is this subscript rho 1. And again, the geometrical factor is as it is. So basically, in this formula now, in this formula for finding out the volumetric flow, the pressure drop is given, the geometrical ratio is given, area at throat is known because we know the diameter there. So we need to figure out what the discharge coefficient CD is and the expansion factor Y is. And we can calculate this rho 1 is also an unknown, but we can calculate it using the ideal gas law here because we are given the pressure and temperature at the inlet. So let's first find out what rho 1 is. So rho 1 is basically P1 divided by R T1, which gives me 200,000 because P1 is 200 kPa divided by the ideal gas constant in 287 in SI units and temperature in Kelvin. So we are given temperature in degrees Celsius, which is 100, but to convert it to Kelvin we need to add 273. So this comes out to be equal to 1.87 kg per meter cube. So now the density at point 1 is known, and also at 100 degrees Celsius the viscosity of air is also known. You can find it from any database. It comes out to be 2.17 into 10 power minus 5 kg per meter second. So the density at 1 is known, the viscosity of air at 1 is known. Let's see what is the value of this expansion factor. Now as this figure shows, the expansion factor depends on P2 by P1 and the geometrical ratio beta. So here our beta is 0.6, so we need to look along this line, and from here you can see P2 by P1 is basically 140 divided by 200, which is 0.7. So basically 0.7 and beta is 0.6, so it comes out to be somewhere here. So your expansion factor is 0.8. So from above figure, Y is basically 0.8 for P2 by P1 equal to 0.7 and beta equal to 0.6. Now the mass flow rate m dot is basically density times the flow rate, which is, if we substitute this here, we will get m dot to be equal to this quantity. So m dot is basically CD times Y times 8 throat square root 2 rho 1 P1 minus P2 divided by 1 minus beta raised to 4. So again here everything is known. We just calculated y, area at throat is known, which is pi small d square divided by 4. We calculated rho 1, the pressure drop is given, beta is also given. The only unknown here is the discharge coefficient CD, and it is not given to us. And if you look in this graph, the CD is a function of Reynolds number, and because the flow rate is unknown, the velocity in the pipe is also an unknown. So we don't know the Reynolds number beforehand. So what we'll do, we will just guess some value. So a good guess seems to be, I always like to start with a Reynolds number of 10 raised to power 5, because it's just a good round figure. And from here, let's say we assume a coefficient of discharge to be 0.95, and we guess that the Reynolds number is 10 power 5 in the duct. So I'll just write guess CD to be equal to 0.98, because, and RE to be equal to 10 power 5. Then by substituting these here, you'll find out that m dot is 0.98 times 0.8 times pi by 4 into small d square, which is 0.06, 6 centimeters square, square root 2 times 1.87 kg per meter cube. P2 by P1 is 60 kPa. So basically 60 times 10 power 3 pascals divided by 1 minus 0.6 power 4. So 0.6, beta is 0.6. And if you calculate this, m dot comes out to be equal to 1.13 kg per second. So this is the guessed mass flow rate through the pipe. Uh, Remember that this is just a guess, because we have guessed a value of CD and a value of Reynolds number, and we don't exactly know. So to find out the exact value, we will have to iterate. So now we have a estimate of the mass flow rate, and if you find out the Reynolds number from here, so your Reynolds number is basically rho v d by mu, and if you just look here, so velocity is nothing but mass flow rate divided by rho times area, and which is basically mass flow rate divided by rho pi by 4 d square. So if you substitute it here, you'll find out that Reynolds number in terms of mass flow rate comes out to be 4 times the mass flow rate divided by pi mu d. And again, if you substitute these values, so 1.13 for mass flow rate, mu is known, so mu is this value for air at 100 degrees Celsius, and d is given 6 centimeters. So 4 times 1.13 divided by pi. I'm just omitting the units here for convenience, but you should always write the units so that you know you're not doing anything wrong. So RED estimated comes out to be 1.11 times 10 power 6. So the assumed RE is 10 power 5, but the calculated RE comes out to be a larger value, 10 power 6. So our estimation was a little bit wrong. So we estimated CD to be this, but the calculated comes out to be this. So let's just guess the new CD to be, sorry, new CD to be 0.99, which corresponds to a Reynolds number of 10 power 6. So in the second iteration, I'll write it correct CD and RED. So I'll guess now RED to be equal to 10 power 6 and corresponding CD is 0.99. And if you repeat this procedure again, for these new values, so m dot is CD times Y times AT square root 2 rho 1 P1 minus P2 upon 1 minus beta raised to 4 with a new CD, so CD is 0.99 now. You'll find out that this comes out to be equal to 1.14 kg per second. And again, if you find out the Reynolds number for this mass flow rate upon pi mu d, it comes out to be closer to 10 power 6. So our iteration procedure has converged. So we started with a guess Reynolds number, and from there we found out a guess CD value. But after doing all the calculations, it turns out that the velocity that we calculate or the mass flow rate that we calculate, it corresponds to a higher Reynolds number. So in the second step, we correct our guess for the Reynolds number and make it a higher value, 10 power 6. And from the chart, we also find the corrected value for the discharge coefficient. Then we again repeat calculation for the mass flow rate, and this time it comes out to be 1.14, which gives us an accurate value for the Reynolds number as well. So this is the final answer. So m dot, that is the mass flow rate through the pipe, is 1.14 kg per second, which corresponds to a Reynolds number of 10 power 6. And again, the one important thing that we learned in this problem is that if the pressure drop is significant, like more than 1 to 5%, here it was 30%, then we need to account for the compressibility of the flow, which is this compression factor, which is again oftentimes tabulated in terms of this pressure ratio. So yeah, that's it for this problem.